In this lecture video, we're obtaining and plotting inverse of a function algebraically. Our objective here is to plot the inverse of a function by using algebra as a tool. So this example is taken from your book. You could browse your book for this page. It's on lesson 1 dash. It's on the lesson 1-5 of chapter 1. So this example number 3 is where our function is equal to 3x plus 12. This is a linear function to begin with. Linear function following the general form y is equal to mx plus b. We could easily say that our m is this, which is 3. This is our slope, and this is our y-intercept. Okay. So our objective, first objective, to find the equation of the inverse of f. Plot the function f and its inverse on the same screen. So how do we do that? First, we define our function. What is our function? Our function here is, of course, the given. So y is equal to 3x plus 12. Let's make f of x is equal to y for simplicity. Okay, our inverse. What is our inverse? Our inverse is then x is equal to 3y plus 12. To invert a function, okay, to invert a function, just interchange the variables x and y. So in this case, just interchange the variables there. We have x and y there. Let your y now become x, and then your x become y. That's how we invert a certain function. And so the third step is to solve the equation x is equal to 3y plus 12, our inverted function, into y again. So we have to get this this term here, y. We have to isolate it, and we have to express the whole function in terms of x. Therefore, how do we do that? So x minus 12, by transposition, we could easily move 12 to the opposite side. It's a property of transposition. So x minus 12 is equal to 3y, and divide both sides by 3. And we could just cancel the 3 on the right side, and that will give us the inverse function y, which is equal to 1/3 x minus 4. This is the inverse. And this is our original function. So how did we get this inverse function? We just transform the equation so that y is in terms of x. So now this is the graph. Okay, how did I do this graph? Okay, let us graph both of the equations in there. So what's our equation here? Y equals 3x plus 12. So let's have y is equal to 3x plus 12 here. And we also have the other one. We have y. Well, let's call it y1. This is y2. So y2 is equal to 1/3 x minus 4. So this is our inverse function. Now, how do we graph this? The simplest method to graph these linear functions or lines is to get the x and y intercept. How do we get the x and y intercept? For example, in the first one, to get our x-intercept, let y equal 0. Or set y is equal to 0. So now our y is equal to 0, or y1 is equal to 0. So that 0 equals 3x plus 12. And solving algebraically, our 3x is negative 12, and our x is equal to negative 4. That's our x-intercept. This is the x-intercept for the original function 3x plus 12. Now, where is that? Let's have a grid and take a look. So I'm going to arrange this such that it tallies with the grid lines. So here you go. Okay, the original function seemed to be here because the x-intercept is at x is equal to negative 4. And our y-intercept, let's do our y-intercept. How do we do that? To get the y-intercept in the first function, we have y-intercept by letting x is equal to 0. Therefore, when x is equal to 0, this one becomes 0 also. So y is now equal to 12. And where is that function? The function seems to be, or the point seems to be in here. We have 0 and 12. The pair of or the point is 0, 12. Now that's how we deal with the first function, okay, with the first linear function. Now we go to the second linear function, which is the inverse of the first. So getting the x-intercept of this one will give us x-intercept would then be when y is equal to 0. So that would give us 0 equals 1/3 x minus 4. And 4 is equal to 1/3 of x. Again, transposition. And multiplying both sides by 3 to get rid of the 1/3 here. Our x is equal to 12. That's our x-intercept. Okay? So as we can see here, that it's here. It's our x-intercept. And our y-intercept is when we set our x is equal to 0. So if x is equal to 0, then our y, this one becomes 0, equals negative 4. And this happens to be below. And this thing is actually here. Okay? And then just connect with a straight line. Connect the 2 points, and then we get the graph for the original function. Our y1 equals 3x plus 12, the original function, which is denoted by this graph. Y equals 3x plus 12, and this is our f of x, and this one will be our f negative 1 of x, denoted by y, let's say y2, not to be confused, this is y1. y2 is equal to 1/3 x minus 4. Now both of these are linear functions following the general equation y is equal to mx plus b. If you notice, both of them are linear functions. So this is the graph. Okay, the big thing here that you see is the graph of this equation, this thing. Okay, this is our graph. And why do we need the middle part again, the line y is equal to x? Y is equal to x shows the symmetry between two inverse functions. It shows that they are mirrors. As you can see, it's like cutting it's like there's an angle here. Okay, from if we extend this one, these two are going to meet somewhere. Okay, let's have, if we extend, okay, then this is going to meet somewhere, and if we extend this one also, then it's going to cut the angle formed by these two lines, by the intersection of this from the intersection of these two lines into two. Therefore, they are mirror of each other. Okay, so much for that. We go to letter B. Explain how you know that f is an invariable function. Our f again, our f of x is equal to 3x plus 12, and our f negative 1 of x is equal to 1/3 of x minus 4. Now these two are invertible functions, because what's our requirement again for invertible functions? Our first requirement is they should be 1-to-1. Now generally, okay, linear functions are generally 1-to-1. Because as you can see, obviously their graphs are just a line. So the graphs are just a line. So there could be from here, that's y is equal to x. That's a linear function. It's a line. It's strictly increasing. Now we have another one here. This is some form of y equals mx plus b, or y1. And then there's another one here. And what else? There's another one here. This is y2 equals mx plus b. This is y3 is equal to mx plus b. As you can see, all of them have this pattern of either strictly increasing or strictly decreasing. In the case of this graph, the first one, in the case of this graph, this is strictly increasing, because as it goes up, it increases. The slope is increasing. Okay, if your line is going up like this, is slanted like this, then the slope is increasing. Also on our y is equal to x function, this is strictly increasing. Now if my y2 equals mx plus b is something like that, then it's strictly is it strictly decreasing or still increasing? Okay, because it has this slant going there to the positive x-axis. Okay, now this one is strictly decreasing, because the slope is going, it's decreasing down, it's going downwards. Okay, and when you have this slope, it's decreasing. When you have this slope, it's increasing. Okay, so explain how you know that f is an invertible function. That's the answer. It's a linear function, and linear functions are generally 1-to-1, or strictly increasing or decreasing. What else? This too follows the general form y equals mx plus b. Okay, and these two are inverses, and they are functions also, inverse functions of each other. Now we go to letter C. Show algebraically that the composition of f negative 1 with f is f negative 1 of f of x is equal to x. Now let's show that graphically. Okay, we have our y, that's the original function, 3x plus 12, and our inverse, f negative 1 of x, this is f of x, is equal to This is 1/3 x minus 4, right? Let's confirm. Yeah. Okay. So we have these two functions here, and we're going to investigate if the composition of functions of the inverse functions have the composition has a property attached to it. So let's get f of -1 of x, for instance. What is our f -1 of x? That would give us f of 1/3 x minus 4, right? So that's 1/3 x minus 4. I want to use green here. So 1/3 x minus 4. And we're going to substitute this 1/3 x minus 4 on f of x. So that would give us 3 times 1/3 x minus 4 How come it's a different color now? Should be pink. It should be this. One-third x minus 4. So like that. Plus 12. Let's investigate. So this one becomes 3 over 3 x minus 12 plus 12. So this is equal to x. And then cancel, cancel, cancel. So this is equal to x. So we have proven f of -1 is equal to x. So f of -1 of x is just equal to x. Now let's prove the other one. Okay, we have our f -1 of f of x. So our f of x here will be the one to be substituted in the variable x on f of -1 of x. So our f of -1 of, what is our f of x? 3x plus 12. That's 3x plus 12. And that's equal to, our f of -1 is 1/3 of 3x plus 12. 3x plus 12 minus 4. So that will give us 3 over 3 x plus 12 over 3 minus 4. So that's we can cancel 3 over 3. This becomes 4. 12 over 3 becomes 4, and 4 minus 4 is equal to 0. So this gives us the function f -1 of f of x. The composite function f -1 of f of x is equal to x. Therefore, we have proven this property that f of -1 of x is just equal to x, and f -1 of the inverse function of f of -1, which is equal to x also. Okay? The triple dot here is just a statement for conclusion. So that's just a statement for conclusion, meaning that we have succeeded in proving what we wanted. So this just means that it's actually therefore, or just a conclusion. Okay? Therefore, f of negative 1 of x is equal to x, and f negative 1 of f of x is equal to x. So what is the conclusion here? That for composite functions of inverse functions, or in other words, when we compose inverse functions, the answer is only the value attached inside, so the value which is to be substituted. In this case, it's x. Okay, so we've got a summary here for function inverses. Number one, the inverse of a relation in two variables is formed by interchanging the two variables. So why is it a relation? A relation could be a function, but a function cannot be a relation. That's why the general term for a function is still a relation, but a relation cannot be a function. That's why the general term is relation. Okay, it's formed by interchanging. Don't forget this. Interchange the variables. Okay, when we want to do it algebraically, we interchange the two variables x and y. X becomes y and y becomes x, and then we solve for y in terms of x again. The inverse of function f is also a function, then f is invariable. This is very important. If the inverse of a function f is also a function, meaning if it's one-to-one, then f is invertible. Now if f is invertible and y equals f of x, meaning it's a function, then you can write the inverse of f as f negative 1 of f of negative 1 of x. Now the f negative 1 shouldn't be confused. F of negative 1 shouldn't be confused as an exponent. Okay? This is just a notation, a symbol for inverse, which is not equal to 1 over f. That's a similarly different term. Okay? F of negative 1 here is just a notation for inverse. To plot the graph of the inverse of a function, either interchange the variables, solve for y, and plot the resulting equations. That's the one we did using algebra. Plot the intercepts. That's the one we did here. I mean here. Okay? And which is actually here. So the one we did here is is getting the intercepts to plot the graphs of the linear functions. Okay? Or you can use the parametric mode. Now you have your grapher. You could use the parametric mode of your grapher to graph those functions. If f is invertible, then the compositions. So this was the one this was the last one we dealt with. Okay. So if they are invertible, then the composition f negative 1 of f of x is just equal to x, provided x is in the domain of f, and f of x is in the domain of f of negative 1 of x. Now this just means that, we have f of f negative 1 of x. So our f of x here, or f of negative 1 of x, is in the domain now of our composed function f of negative 1 of x. So this is the function f negative 1 of x is in the domain interval. For example, we have 7 and 1. So our f of negative 1 of x would now be inside the domain of our x. So something like that. Okay? And vice versa. It could be f of x if the domain for f negative 1 of f of x, because our f of x then now is the inside function. So it could be in the domain of our f of negative 1 of x. Our f of x is in domain of f negative 1 of x. For example, the domain of our f of negative 1 of x is from negative 2 to 5. Then f of x should be inside the domain interval from -2 to 5. And lastly, a one-to-one function is invertible. I have always emphasized this. A one-to-one function is invertible. It's strictly increasing or strictly decreasing functions are one-to-one functions. So this ends our discussion and lecture for inverse of functions, lesson 1-5. I hope you gained a lot of information on this, and thank you for listening and watching, and have a nice day.